quite a bit. All right, so we are recording. So I'm actually going to use the whiteboard to go over this first. This is actually a pretty fundamental concept. There's like a duality here, okay, in how in neural networks. There's basically this concept of going forward and then going backwards, right? And those two things we need to understand. So right now I'm just going to start talking about the going forward part. Okay. All right, so let me grab my pen here. All right, so we're going to start with a simple operation that you guys have done already in NumPy. You did these exercises in NumPy at the beginning of the semester, and you did these operations, right? These are necessary that we understand these operations of vector and matrix multiplications, okay? But you can think of them as any algorithm, right? So, these are coming from an area of math called linear algebra, true, but linear algebra is very broad, right? And this is only like 5% of all of linear algebra. It's really what we need. So you can really try to understand this technique as just any algorithm, just like you understood how to do sorting when you did data structures, or you learned how to do this or that, right? That's kind of how you need to approach this, okay? So I'll start with some manual operations of this, just kind of how it works. And then what I want to show you is how this is important to understand a neural network, okay? The intuition of these ideas. And then we're going to like compare this to our, we're going to do this in PyTorch basically and compare it to our code to see how what the code gives us basically, okay? So it's all about vectors and matrices nowadays in machine learning. It wasn't like this, when I first started in machine learning. I did a whole bunch of for loops. Very inefficient code, right? But it just changed. Why did it change? That's why I gave you that history and the context on Tuesday, right? What was the reason? Happened in 2007, GPUs for computer graphics, right? From there, people were already doing the math but once the GPU became a thing that it takes you a week to train a neural network versus 2 hours, you're going to immediately go to the, if I give you a Sci-Fi 10 homework and it's going to take you 3 days of you being there, eventually, and it breaks all the time, every time you have to debug it another 3 days, eventually you're going to say, no, I'm going to do the other approach that takes an hour. You see that? And so we want to understand this fundamental concept of the GPU and what it does, right? So I'm just going to start with a very basic example here. I have a function that takes in a value, which is going to be a vector. A vector is just an array. So instead of always thinking in terms of one variable and one value, we're always now going to think of a variable that is actually an array with multiple values in it, and processing these values at the same time in parallel. And that's what NumPy is. You've already seen that. That's what Torch is. You've already seen that, and so on. All right, so I'm going to give you a very basic one here. I'm just going to say I have a vector like this, 1, 2, right? And then I'm going to say plus v. So that's the function. So then the input to this will be another vector, right? So I'm going to do here an example. So f 4, 4. Right, so I'm just laying down the background, so that we can build the neural network. So in this case, then we're just going to use this function, right? So it's going to be 1, 2 plus 4, 4. You guys see that? So basically, that's the operation that's happening there. Okay, just changing color. So then this would be what? This will give us a vector like this, where you take 1 plus 4 is 5, right? And 2 plus 4 is 6, correct? And that's the answer. So you just basically, like think of these as algorithms, and you just have to know you're doing this for the KNN. This is why I gave you the KNN, because I figured you'll visualize that, you'll see those images and what happens when you average them, and you understand. Okay, so this is one simple operation, right? Just to kind of get started. Let's do another example of the same thing. So I'm going to do here f, and I'm going to plug in there -4, that. So this is once again 1, comma 2 plus v. So v in this case would be -4, comma -4, right? So you're doing this in parallel here. So this is going to be 1 -4, comma 2 -4, right? And the answer then should be -3, right? -3, and then -2, right? And that's your answer. Okay, so this kind of defines the space that we are working. Okay, we're always trying to do these things in parallel. Because here I have two of these, but in your examples, you have 200 by 200, or you'll have even more, data points. So that's it's like that. Pretty simple, right? Pretty easy. Okay, now let's look at, now when is this relevant, what I just did? This is actually relevant in the neural network. The neural network has the very, very simple formulation of something that you already know from high school, which is the formula for a line. You guys remember the formula for a line? Mx plus b. Do you guys remember that one? It's funny how it all comes from that simple concept, right? So if you guys remember mx plus b, you see that? Okay, well, this operation that I did here, right, that seems like I'm just doing something very trivial, is actually happening in the neural network. Basically, it would be the FV would be the mx, and then the plus b is what I just had. Do you see that? So neural networks, you'll see me write this equation a lot. We can start here, and then we're just going to build it up. Okay, but this is important because what does that tell you? It tells you that this is going to produce, let's say, two things, which in this case would be 2 neurons, let's say. And then you're going to need to add to those 2 neurons these values, the biases, 1 for each one. See, so the operation is like that. Does that make sense? All right, so that's why I did that. Okay, now let me move here. So once again, this is the formula for a line, but we're going to change the formula a little bit to become MW, this is a W, plus B. Okay, so once again, sorry, the M is what I should have changed. Sorry. So the M is W, and then this is. All right, so in a neural network, what you're basically learning is a function that predicts given an input. Remember your X and Y's? That's exactly what we're doing. So you give it an X, it predicts a Y, but we need to learn W and B. These are generally called the parameters together. Okay, and we're going to see how in the model, we want to always know about these parameters. Now, in this example, there's only one W, but when we have really big neural networks that are very deep, there's going to be, people will say 7 billion parameters. And when they say 7 billion parameters, they mean 7 billion parameters. So maybe you've heard of this, like they talk about GPTs and they say GPT 7 billion versus GPT 65 billion. And what they mean is literally one has 65 billion parameters, the other one has 7 billion parameters. You can see once again why you need so much computing power to learn this. Right here we have 2 parameters. Okay, but anyway, so this is something that we'll, as we start building more deeper neural networks with more things, we'll start printing out, okay, this one has so many parameters, and so on. Okay, but anyway, we performed this operation. I showed you already basically a simple sum of vectors. Okay, and that's this one plus that. So now I'm going to look at this operation, the MX, right? And once again, yes, it comes from linear algebra, but we can think of this as just an algorithmic approach. There's actually a mechanical trick that you do with your hand, it's like instinctively when you're doing this operation. So I'll show you guys, and it's like an algorithm type of a thing. So let's do a simple example here. This is going to be example 2. This is going to be called a matrix multiplication, okay? Oops. Matrix And this is important because, again, this is another part of the neural network. This is the matrix multiplication. You will see once we get into the code, I will be using torch matmul. So torch matmul, torch is going to be like NumPy, right? So as we do NumPy, now we're going to use torch to build our tools. And we're going to say torch matmul A comma B, for instance. That operation is basically what I'm about to do here, just to kind of show you how it works. It is fundamental. It is like the operation. In PyTorch, it is the operation in deep learning. Why? Because that's what the GPU does, like physics. Does that make sense? So that's what we need to understand. All right, so I'm going to just take two variables here and just do a simple operation. So I'm going to do x equal 1, 3, right? X, 1, 3. And then I'm going to do a matrix A, which is going to be 2 minus 1, 1, 1, okay, like that. So this is the operation that we would perform with the neural net, okay? So how do we do this? I'm going to say y equals A X, right? So, and I'm just going to write a symbol right now, and let's call it a dot, but it represents that matmul operation. It's not a pixel-wise multiplication. It's not, it is a matrix multiplication. And think of it as an algorithm that has rules on how the multiplication should be done, okay? So that's what I'm going to show you, the trick of how to do it. All right, so here we have 2 minus 1, 1, 1, and then 1, 3. All right, this is what I'm going to multiply. Okay, and later on, we're going to start to see that the neural network does this, that it has meaning. All right, there's meaning. And interestingly enough, it's a type of a vector space meaning once again, okay, which in the neural networks environment is called embeddings. So they don't use the word vector space, but they'll use the word embedding. It kind of means, you know, something similar. Okay. So then I'm gonna do this and that. Okay, and I'm gonna do this and that. So what do I mean by that? I mean I grab the 2 and the 1, and I'm gonna multiply it by the 1 and the 3. So what this represents is that they're the same size. You see that? That has to happen. If they're not the same size, this does not work. They need to align in this operation. Okay, so what I mean here is this one and that one, and perform that as a multiplication and then a sum. That's the algorithm. Okay, so let's go ahead and do that. So I'm going to do here, just the answer to this, by the way, should be, just so kind of you have an intuition, 5 and 2. That's what it gives you. Okay, that's the answer basically. Okay, so let's move on over here and do the actual operation. So I have enough room. So 2, 1, minus 1, 1, 1, 3. Okay, which needs to result in 5, 2. Okay, so this is going to be then 2 times 1 plus 1 times 3. Do you see that? So I'm taking this one times this one, but I multiply this times that, and I multiply this times that, and then I add those results together. That's the matrix multiplication, the famous matrix multiplication that is used heavily in deep learning. That's it. But this is very important, okay? And it doesn't work, obviously, if this is a 1, 3, 7, and this is just 2, 1. It won't work. So you have to, and that's actually important. So let's do the bottom part. So then I would do minus 1, 1, minus 1, 1 times 1, 3, right? So I would do this times that. So we can do that down here. Minus 1, 1 plus 1, 3. Do you see that? And once you perform this operation, let's kind of do it further. So 2 times 1 is 2. 1 times 3 is 3. So that's plus. And then this one, minus 1 times 1 is minus 1. Plus 1 times 3 is 3. And now 2 plus 3 is so 5. And minus 1 plus 3 is 2. Do you guys see that? That's it. So again, treat this as an algorithm, and there's just a couple of rules that you follow, and it always works, and you always do it. And this is the part that is happening in the neural network, and this is what I'll show you in a little bit. Okay? Any questions about that? Does it make sense? Okay, that's the matrix multiplication, okay? Another thing that, just to kind of to do an exercise, sometimes you want to flip things, like you want to flip around the matrices. You might see me do this at some point later in the semester. So this is going to be another matrix. Let's say it's just an example: 1, 3, 5, 2, 4, 6. And then I'm going to do what is called the transpose of this. And basically, I just want to like rotate this so that I can align it to what I want to do, okay? This is important because sometimes you multiply an x times a w, but the w has no values that have meaning because those are actually the weights that you want to learn. So initially, it doesn't matter what they are. They're zeros, random. As the model learns, right, they will become meaningful. So the trick is to rotate things in such a way that you get what you need to get, okay? So we'll see that in a sec, but I just want to show you this operation here. And stop me, please, if you have any questions. This is if this class is called Machine Learning Foundations, this is a very foundational concept to understand. So now I'm going to transpose it. So I'm going to do this, that, this, and that, this, and that, right? So that means I'm going to grab this 1, 2, and I'm going to make it 1, 2 like that. Then I'm going to grab the next 3, 4, and I'm going to make it 3, 4, and I'm going to grab the last one, 5, 6, 5, 6, and I'm going to make it 5, 6. You see that? This is another operation that I'm doing. And it's another algorithm called a transpose algorithm that performs this rotation. And so, because you know that it does this, sometimes you may need to rotate things, and you can do it this way quickly, okay? So anyway, those were just some operations that I wanted to give you as basis. Now, let's get into the neural net, okay? Let's think about a neural network and how these things tie in. All right, so let's create a new one. So I'm going to draw a neural network here, okay? I'm going to use something that you have used before. Iris. This is why these data sets are so useful, because you've used them before, you know them, right? So what do you know about Iris? 150 samples, 4 features, 3 classes. We know that about Iris, right? And you use MLP. I'm going to build an MLP. Okay, so MLP. But we're only looking at like the operations and what everything means. So I'm going to build a neural net here. Iris has 4 features. That means 4 neurons, okay? Even though there's 150 samples, we don't care about how many samples we have in our setting up of the code and setting up of the diagram. What we do care about is the number of inputs that it has. So this is called the input layer. And this is basically X. Do you guys see that? Now I know that the output is over here, right? This is also pretty important, is the Y, the output. How many outputs? 3, the 3 classes. So whenever we have multi-class, we have basically, if we have 5 classes, 5 neurons. The only exception is when we have the binary problem, we can have 2 neurons or just 1, because if you think with 1 neuron, it can be 1 or 0. So effectively, it can capture both classes. So that is possible. But in general, if we have multi-class, then we do it like this, okay? So this is the example. All right. So now, for the multi-layer perceptron, we want to create the hidden layer, right? And I'm going to create, just because, a hidden layer. I'm going to call it hidden layer 1. And I'm going to say that I want it to have 1, 2, 3, 4, 5, 6. The code that I provided is like this, so I want to be consistent, right? So that you have, oh yeah, please.
Is there a reason why it's 6, or is that just like that you pick, like,
I picked this. You know why I picked 6? Because I'm about to draw all the connections, and I did not want to draw that many connections. But I also didn't want to do 4 because this is 4, and I didn't want to do 3 because this is 3. So I should have picked 5, but I picked 6. So it's only because I'm about to draw these connections.
Oh.
But otherwise, I mean, it's the architecture. So you guys should choose. Iris doesn't need much. That I can tell you. So something like this. You could pick 4, 3. I mean, it doesn't need much. Okay. Any other questions? So yeah, so I picked 6 just, again, you're about to see me draw all these connections. So basically, we can have neural networks that are not fully connected. But in general, whenever you start, you build neural networks that are fully connected. What that means is the following. So the definition of fully connected neural net means literally this. This neuron is connected to that. You see that? And then all neurons are connected from one layer to all the neurons of the next layer. All right, so now I have this other one. Right, and then the next one. You see that? And the last one. That's what a neural network is right here. There's only one component that I'm skipping, which is the activation functions. We'll add those later. These are basically linear models currently. They become nonlinear when they have activation functions, but that would complicate things. So I'm just keeping it simple right now. Do you see that? This is a fully connected neural network. That means every neuron is connected to every single other. Yeah.
She's about to ask that.
That's what yeah. Okay, yeah. So that's what it means. Now, these are the parameters that we are learning, and this is denoted by that W. So if you remember in the line, the M is now the W. So this is going to be W, and I'm going to label it W0 for a specific reason. Okay. The operation that I did at the very beginning, this one, right, of the plus V is important here. It's the bias of your line equation, which you know what that is. So what that means is that for this example, this is going to give you 6, right? Six numbers, and then you're going to add to it a vector of 6, which is the biases for it. Okay, so that's basically all it means. So you need to have you're going to learn these values, 6 values, which would get added here. But before that, you also need to go from X to W to get these values here. Do you guys see that? Does that make sense? Questions? So yeah, so I'll erase this because this usually is omitted when you look at neural networks. And so you may think that it's not there, but it's omitted so that it doesn't become complicated, but it is there. I mean, you can choose to remove it if you want in the code, but in general, it should be there. Yeah.
After each layer, you add your bias.
Yeah, exactly. You add the bias here. So if you have 6 neurons, 6 biases. If I have 17 neurons, 17 biases.
And then if there was like another layer,
you can another bias. Yes, exactly. The bias
out.
Hmm?
I'm assuming they're like it's like a real it's like a scalar.
Those are the values that get calculated. So it's that you create the equations, you build something called a computational graph, which captures all of this. And in backpropagation, those values are going to get updated. So that's how it happens. So, but in neural nets, those things are usually omitted, okay? In the diagram foremost. Does this make sense, guys? Now, I want to give you a very important insight right now. another matrix is happening here, which is this one. W0 actually has shape. And the shape of W0 is sorry, that came out a little squirrely. What is this? This is x1, x2, x3, x4. Why? Because you have x1, x2, x3, x4. Do you see that, guys? And then here, then, you have 6 weights. So that intuitive, but it's weight zeros, right? So I'm going to call it weight 0, 1. Or, well, okay, start at 0. Weight 0, 1. Weight 0, 2. Weight 0, 3. Weight 0, 4. Weight 0, 5. Do you see that? So there's 6 neurons here, 4 neurons here. This is another reason why I selected 6. I didn't want to make such a big matrix. But this is happening in the neural net. So you have 4 rows and 6 columns because you have 4 inputs and so this is the weights matrix between one layer and the next layer. Got it? And so that tells you that what? This is going to be a value. This is going to be a value. All of these initially, when you initialize this, they can be random values. But as you train, these values become important. That's the whole pay attention thing, right? So it might be that feature 3 and weight 0.02 becomes like a 0.7. It's an important one. But another weight like x2 and this weight is like almost 0.001. So it's not important. How do you assign these values? This is literally the neural network. That's the intelligence. Elon Musk made the joke the other day that people are afraid of AI, right? Of ChatGPT and all that. And basically, he just said people are just afraid of a file full of weights. Think about it. If you're afraid of just this, just a gigantic one of 7 billion size, but that's what people are afraid of.
AI is scared of Elon Musk.
But no, that was a joke that he said, but it's actually very interesting, right? That he said it's just a file with weights in it. And then those weights get loaded into a neural net and you have given inputs, outputs. And that's what people are afraid of. But it's really just a file of weights. That's AI, really. Okay, because that's the thing that you learn in the architecture you define as well. Okay, does this make sense, guys? So if I had MNIST, this would be 784, and then maybe I do a layer of 100 neurons. So this 784, 100. You can see that's a lot of weights. You see that? Now imagine a really large 4K image that you don't downsample. How many weights is that? You see how it explodes if you're not careful with the size of your files. Okay? All right. But anyway, so this is very important. So that's the W0 weights is basically a matrix that we're going to learn. Okay? Then over here, also these are going to be connected. So I'm going to connect these. Right? So like that. So I want to connect. These connections just represent the values that are in that, oops, sorry. In that weights matrix. Then I'm going to do this one. And that just means fully connected. As you can see, as this explodes in size, it becomes impossible to draw these. I don't know why it's like curving. There you go. So that's a fully connected, I'm only going to do this one time, but that's what a fully connected network is. And basically then, what would that tell you? There's another matrix, right? I'm just going to do the numbers this time around for W1, which would be what? 6 to 3. Do you see that? Does that make sense, guys? So now you take the X's times these W's to produce the next layer. So you're going to multiply this times this to get this. And once you have that, you take this times this to get this one. So in essence, all you're doing is transforming your data from one vector space to another vector space. I don't know if you see that connection yet. We're going to see it in a second, but you're literally, it's like you're going from that KNN of 4 to 3 to, in this case, actually, we're going from 4 to 6 to 3 for all 150 samples or all 120 samples, okay? So hopefully that made sense. So this is W1, okay? Now, also in the code, actually, you write this out more like functions. So it's going to be, now that you hopefully understand, everything is going to be W0, that's these weights, right? Matrix multiply, so that's the operation that I showed you a few slides ago, times X, which is another matrix of the data in this dimensionality of 4, plus the bias, which I already stated, should be a vector of size 6, right? And what is this equal to here? What is this equal to? H1. Do you see that? So you just jump to the next layer. That's the feed forward. You go from one to the next and then to the next. And imagine if you have 128 of those and then back when you're training. Okay. So now what about for the rest? Because you want to get to the output, right? The output is over here. So the output is Y, right? This Y. So I'm going to say now Y, and I'm going to ask you to tell me. And then let's assume the bias here should have been B0 to be consistent, because this is W0. All right, so then what is this one? What are the weights here? W1, okay, W1, it's matrix multiplication. And this one should be easy, B1, right? What is this one? H1, very good, exactly. Perfect. You see that, guys? So you produce this one, and then this one becomes the input to the next one. That's a neural network, literally, in essence. And you write it out as this function. So then the key question is, just focus on, we're just going to focus on X and H1 here. So just this one, right? So I'm going to maybe use a different color here. So now I'm going to just focus on this part. And literally, since I know these are matrices and things like that, I'm going to do that matrix multiplication operation that does all the heavy lifting for us, right? This is what the GPU does, like in seconds, right? Or nanoseconds. So, okay, I'm going to draw it here in a different color. So now we need to know that the X is going to be this one, right? So this is X. I'm going to draw the X inside. It's going to have 4. Why? Because the inputs are 4. It's iris. So you know there's 150 samples. 150. Do you see that? What you want is, since you're running 100, I'm using iris, all of the samples as 150, but this term will change in the neural network, and it will be called the batch size. What that means is, you know, let's say you have 1 billion samples. You can't give, you know, regardless of how many GPUs you have, you can't give 1 billion samples to a GPU at once. You just don't have enough RAM, right? So what you do is you break the data in batches. You're going to give it 64 and then 64 and then 64. So there you use a for loop. You grab a batch of 64. Boom. So that's kind of like this. So imagine I'm using iris just because it's more intuitive, but really this could be the batch size 32. So I'm giving it 32 samples of iris, or the 150 samples of iris as they appear originally. But I know that I'm building a neural network, and that should be transformed. The data should be transformed into a layer that has 6 neurons from a layer that had 4 neurons. Do you see that? Okay. So I don't know, maybe, what this one is. The W0. I don't know. Let's say for now, I don't know. But I do know for sure that the hidden one, right? This hidden one, which is this neural network layer, should have a dimension of 6 now instead of 4, right? We know that because 1, 2, 3, 4, 5, 6. You see that? But we need to do that for all 150 samples or the 32 samples in the batch. So those still are remain as individuals. It's like they're still individual samples. They're just being transformed from being of size 4 to being of size 6 as they're going through the neural network. Do you guys see that? Think of the example if you only gave it 1. So you give it 1 sample of 4, and now it becomes 1 sample of 6. You're transforming it. Okay, that's what the neural network does. As I said, I'm only doing the linear part. I still need to do a slightly, but that doesn't change this intuition. Okay, so then I know that the output here is 150. Do you see that? I literally transform from one vector space. We talked about this, right? When I said to you, 150 people, all of you here, has jacket, has tennis shoes, is wearing green. That's this vector space, and now you can place everyone in that space, correct? Well, that's this one, only with 4 features. So if you think about it, when we perform this operation of the weights, right, we convert everything into 150 by 6. What did we do effectively? We took all those samples, they were in a space of 4, and now they're in a space of 6. Do you see that? Is that intuitive? That's important because you didn't do that. Who does that? The neural network. The neural network is trying, remember, this is a supervised learning problem. So it wants to classify cat and dog. So it's going to make, remember, it's optimization. So it can choose something here that will take this and give it that. You see that? And so imagine it tries one set and it gets this. But then when it tries to predict cat and dog, what happens? It's wrong. So that's not a good set of weights. Try another. Predict this. Cats and dogs, not correct. Keep doing that. Eventually, it gets a set of weights that when you take this times that, and you get this new vector space, now the result, when you compare it to the real, is good. And so it knows that those are the right weights. That's basically all that's happened. So now just think about this. We know the dimensions of this. We know the dimensions of this. We just have to figure out the dimensions of W0 that when we perform the matrix multiplication, it'll give us this one over here. And that's the operation that I just showed. You guys see that? So I'm going to do that now. Any questions? Yeah, Henry, go ahead.
Why is machine learning hard?
Well, come on, Henry, come on. Let's see that. All right. Anyway, this is just intuition. You're not coding this from scratch, right? But I'm just trying to give you the intuition of the vector space. So the weights matrix, actually, it's not something you have to figure out. That's also the beauty of PyTorch. You just build this. This is more intuitive to you guys, right? But what's happening in the background is this one over here, okay? Because the GPU is going to take this, the batch of 4, times whatever this is and produce this new batch. And it's just going to keep doing that. If you have 128, does it, then again, and again, and again. It's transforming everything until it eventually, predicts the class. So now, the size of this one should be 4, 6. That's actually the number of weights that you need to calculate, okay? Which, as it turns out, is this one, right? These values in here, okay? But you don't need to figure these out anyway. But I'm just going to show you that when you make this multiplication from this one with this one, you get this. Okay, so that's the next step. All right, so now let's start over here. So we have 4, 6, right? That's the W0. Okay, so now I'm going to perform that operation that I did before. Right, I'm going to do exactly that, and you'll see that you're able to create that. So you have 154. So each one of these, as you know, is a sample. One sample of 4. And then the next one, another sample of the iris data set of 4 features. You're going to perform, I'm going to use this symbol to indicate matrix multiplication, what the GPU does. And in PyTorch, matmul. That's all you need to know. All right, so then I'm going to do, now I'm going to write this out. And I'm transforming. This is going to be 150, but now I want the representation of this row, which was 4, to be 6. Intuitively, you could say it's like I'm extracting from the 4 new concepts and I'm making it 6. You see that? You could say that, like if it's like height, but really it's not tall and short, it's tall, short, and medium. So I need to extract that out. And so I'm going to add a new 2 new neurons that capture it. So let's take a look here. So this one, we already established that this is 4 by 6. How do you know this? That's the beauty of this, is that, you know, these values initially are random. The neural net, you just set the original, the operation, and the output, right? And the neural network, as it's learning, is updating these values. So the operation here, then it's going to be, since this is 4 like that, this is 4 like that, you see? So there's 4 values here and 4 weights there that initially are random. So when you multiply this one times this one, so I'm going to do that. I'm going to use a different color. Okay, so I'm going to multiply this that has size 4 with this that has size 4. The result of all of that is just one value. You see that? Just one number. But it now becomes the number for the first neuron of the 6. Do you guys see that? And it really, with this operation, then it's always doing this. Try some weights. They don't work. Try some other weights. Eventually, after many, many iterations, it's got the right set of values that when it multiplies these times these, it gets something meaningful here that will lead to better classification. Because remember, you're always predicting something and comparing it to the real. Okay, I'm gonna go back to blue. I think it was light blue, right? Okay, so I just need to write these out. So there's gonna be another one here, 4, but this is for neuron 2, 3, 4, 5, 6. It's almost like you set, I want to multiply x, which has all these values, times this variable, which I don't know what it is. But I know this operation results in these dimensions. So you see how everything is shapes in machine learning, right? I got these shapes with values. I got these shapes. They'll give me these shapes. That operation always is like that. And then in the learning, I just change what the weights are supposed to be. So I'm going to switch to another color now, like this one, purple. So now I'm going to take this same one, right, which is 4, and I multiply it times these 4, the corresponding weights, and that operation gives me one value, which becomes this value. Do you see that? And that's the transformation that I'm performing. And you just do this for all 6, so that eventually you have 3, 4, 5, 6. So effectively, you've converted, by doing this, the sample that had 4 into the same sample, but now represented as 6. That's what neural networks do. Any questions? That's it. That's this operation is what you guys see in a diagram form as this. You're transforming the neural net from here to that. and then to that in such a way that those, by changing that parameter, you improve the accuracy of the model. That's like fundamental. So I'll let you guys digest that idea for a while, but we can come back to it, and I may do other examples. I'll definitely do this in code. But neural net is this, and what sometimes people miss about it is it's really that. Okay, and that's really important because, you know, just to give you an example, this value is always 2, 3, right? Always. But this at first could be 0.1, 0.2. That's what they could be initially because they're weights. So what's going to happen to these values? They're kind of small, right? But as it turns out, for this to be a good classification, these first two neurons should be 7 and 10. Just as an example, that's what they should be to be a good, obtain good accuracy. So what needs to happen? Can you change 2 and 3? No, because that's the sample. That's the actual data. But you can change these two, see, because those are the weights. So now, what would give you, given 2 and 3, 7 and 10? What value should you use here to get those values? Just give me like ballpark. 2 times 3.5, right? And then what's the other one? 3. That gives me 7 and 9. No? Yeah. All right. So you see what I'm saying? So if I get 7 and 10 in the next prediction, I'm going to predict cat, and it is a cat. I compare those two. I got it. But I needed to change, you know, I needed this to be 7 and 10 because this is also going to be multiplied by other weights. This I cannot change because that's just a sample. The only thing I can change is this. So I need to play with these until there's a match here. Initially, in the first example, the intuition should be that you have 0.1, 0.2, that gives you whatever these values are. The real value is cat, but you predicted dog. So these were bad weights. So these were bad weights. Do you see that, guys? And so this is what I want you to understand. You cannot change this, but this you cannot change because this is your X and your Y, but you can play with these weights until eventually you get cat and it's cat, and boom. Those are good weights. Yeah, go ahead.
And the bias in this case would be 0 and 1.
No, these are weights, actually. I'm referring to these as weights. So the bias would be for this operation, adding it here. Like you see these 6, then you have to add 6 bias, one for each, respectively.
Gotcha.
Make sense? Yeah.
I'll need to study this.
Okay. Yeah. So actually, yeah. So you would basically do something like this with a broadcast and broadcast it. The 6 though, this would be 6. So 1, 2, 3, 4, 5, 6. Add it to these 6 and transform that value. You also learn these just like you learned the weights. So that's another vector that needs to be. Okay. So this is the idea basically. Pretty fundamental. So hopefully that made sense. Again, the whole class won't be like this, but this is actually what is happening. Okay, and hopefully this analogy helps. So really, to get this to match, this needs to be 7 and 10, which means we needed the weights to be 3.5 and 3. And then, because this doesn't change when we do this operation, we get what we want. Okay. All right. So hopefully that made sense. So yeah, let me do one more operation, just a simple example. And it's 7:32, so actually we can wrap up with that. Just to kind of remind you with numbers, the operation that is happening. And then on Tuesday, we'll pick up here and do this again, but in PyTorch. I will literally perform this operation because it's iris with this neural network, and we're going to print out the shapes. So I recommend over the weekend, just do this by hand, like do it a lot by hand. So you remember the shapes and what you're expecting. You probably want to see what the shape of this is, the shape of this is. And we'll do it in PyTorch next Tuesday. So I'll do the one final operation, just once again, remind you. So I'm going to do a matrix multiplication. So again, matmul. PyTorch also nowadays PyTorch uses the @ sign as the matmul, but I usually like to use that. All right, so let's take a look. We have 1, 2, 3, and then I have 10, 20, 30, right? So again, you just need to understand this like an algorithm, right? So let's see if you guys get the idea, right? So I'm going to give this as a problem to you. This would give me 19 and 190. You see that? That's the result. Okay. So then what is the dimension of this one? You don't know the values, right? But you know that there's a set of values that will give you this. But what are the dimensions of this? Hmm? 3 by 1, but yeah. Yeah, you're halfway there. Yeah, exactly. Yeah, so this is 3 by 1. Do you see that? Why? To get this one, if you could have tried yours, but then you get another shape, or you could have tried yours and you get another shape, or you could have tried one and it just doesn't work. It doesn't like, it'll give you an error when you try to do that operation. So those are actually the possibilities, error or other shapes. So this one is 3 by 1. So now if we look at it, 7, 0, 4. Okay, we're going to do this and that, and then this and that. So basically, that, and then this and that. So it's important that there be 3 here and 3 here. So there's like a set of rules to these things. Sometimes if you don't get things right, they don't work. But if you do get them right, they work. And actually, it's a neural network also. All right, so you could build a neural network in NumPy, no problem. I could make you do a 128 layer neural net in the feed forward. Your problem is going to be on the back propagation because you're not going to have what you need, the libraries. So now let's do this operation and we'll wrap up with this. So this one will be, so I need to do this and that. So it's going to be 1, 2, 3, and 7, 0, 4, right? So it's going to be 1 times 7 plus 2 times 0 plus 3 times 4, right? And that's kind of the first row with the column. Then I do the bottom one, this one, 10, 20, 30. So I'm going to do 10 times what? 7, right? Yeah, very good. 7. Yeah, see, that's how it is. 20 times what? 0, right? So 20 times 0. And then the last one, then it's going to be 30 times 4. Do you see that? So like this, like that. That helps you. The dimensions need to be appropriate. And then the result of this should be 19, right? So let's work it out. 7, that's 0. So this is 12 plus 7 is 19. And then the other one, this is 0. This is 70. 120 plus 790. Do you guys see that? That's it. This is just treated as an algorithm. You don't have to worry about many other things, but this is fundamental because the GPU is designed for that. And this is what obligates us to do things this way so that we can do things in an hour and not in 20 hours. All right, great. Yeah, so that's actually all my notes for this. And then on Tuesday, we'll repeat this, but in PyTorch. right? We'll go over that, try a few more exercises, and then hopefully start to build up the intuition to start building neural networks. Okay? Great. All right, guys, I'm gonna stop here. Okay. Don't forget to work on your